Hello, welcome everyone. We'll give it just another minute or two for people to arrive. Hi, welcome everyone. We'll just give it 1 or 2 more minutes for the last few people to come in there. Okay, so it's 2 minutes past 1, so I think we'll go ahead. So firstly, just to welcome everyone. Thanks very much for joining us this lunchtime for our webinar. Whoops. Sorry now. There. So just some general housekeeping. So this webinar is being recorded. It will be available on the CIWEM website in a couple of weeks' time after this event. And you can view the past webinars and past digital series at the link provided there. If you experience any technical issues or need assistance, please raise your hand and use from Zoom. And if you've any problem, use the question and answer feature. So we will take questions at the end. So if you could hold any questions till the end, feel free to put into the Q&A chat throughout the talk. But if you're going to put up your hand for questions, I might just please wait to the end.
Hello, Laura. You're breaking up a little bit. You're breaking up a little bit.
Oh, am I there? Okay. So are you, Barbara? So I wonder is my connection. I might go on. I haven't got a whole lot today, to be honest, and if it's very bad, I'll just cut it very short.
Okay.
That's all right. So yeah, so I'll go be quick about this. So yes, each of the talks will be around 15 minutes long, then around 15 minutes at the end for questions. And this event is CPD for 1 hour. So just some very briefly about CIWEM. So CIWEM is a royal charter body and independent charity. There's links there regarding CIWEM, vision and strategy, membership and policy, and then particularly at the end there's some information with regard to CIWEM and PFAS. So CIWEM have a policy position statement on PFAS and also a risk and management in the water industry as well. CIWEM all over the globe, with particularly large membership in the UK and Ireland. So today, welcome to our Republic of Ireland webinar. So the CIWEM Republic of Ireland branch are very big supporters of research and early career research and professionals, and are very proud sponsors of the best water-related prize at the ESAI, so the Environmental Science Association of Ireland Conference. Leila won this prize in 2024 for her submission on PFAS from a source in liffey, which she's going to celebrate. And Leila carried out research in DCU of the EPA-funded Invest PFAS project still going. Also joining Leila is Helen Burke, who is currently undertaking her PhD within the same research group. And Helen is going to share some of her findings on cross-contamination during sampling and analysis and samples. So first we'll pass over to Leila and then Helen. So do you want
Thanks, Laura. So can you see that?
Yep, that's perfect.
Okay. Hi, I'm Leila Bowe. As Laura Foley mentioned, I'm an environmental engineer at Arup, and I'm also currently conducting a Masters of Research at the Dublin City University as part of the Invest PFAS project. It's a EPA-funded, research-funded project to assess the current extent of PFAS contamination in the Irish environment. and to inform a national strategy on PFAS management in Ireland. So my section of the project is determining potential major sources of PFAS in Ireland and the major pathways that the compounds can get into the environment, essentially looking at how they move from source to sink. So this work will inform a nationwide risk assessment to determine the most high-risk uses of PFAS. So in my presentation today, I'll be giving a brief introduction to PFAS and my research problem. I'll be then structuring my presentation using the foundational risk assessment methodology that will be used throughout the research project of source pathway receptor linkages, which includes identifying potential sources of PFAS in Ireland and potential pathways. We're currently conducting a case study in the Liffey Dublin Bay catchment, which will be used to inform and validate the methodology prior to identifying any trends across Ireland. So as many of you are aware, currently there is great interest for international research and regulation of PFAS, such as the current Water Framework Directive Environmental Quality Standards for PFAS and the upcoming Drinking Water Standards in January 2026 for the sum of 20 compounds and total PFAS. So PFAS are also known as forever chemicals, so due to their persistence, bioaccumulation, and inability to break down in the environment. PFAS are a group of more than 4,700 human-made chemicals that have been used worldwide since the 1940s due to their waterproof, oil-proof, and fireproof properties. The most notable of the 4,700 plus compounds that you might have heard of are PFOA and PFAS due to their links to environmental and human health issues, such as neurotoxicity, endocrine disruption, and carcinogenicity. So as shown in this illustration of PFAS compounds typically consist of a fully fluorinated hydrophobic tail or water hating and a hydrophilic or water loving functional head. So the carbon-fluorine bond is incredibly strong, making them resistant to breakdown under natural environmental conditions. And the water-loving functional head means that they can travel long distances. Every single one of these 4,700 plus compounds looks different and can behave differently in the environment, which I'll get onto later. So my research will inform a nationwide risk assessment to determine the riskiest sources of PFAS in Ireland. To conduct the risk assessment, I will need to determine whether there are valid SPR linkages between a source, a pathway, and a receptor. Positive PFAS detections in the environment are an indication that somewhere there are valid SPR linkages. But PFAS is being found across the world, everywhere in small concentrations, including in polar bears in Greenland. So how do we figure out where the contamination is coming from and what uses are contaminating the environment most? So the compounds that we find and the concentrations can give us clues as to what the major contributing sources are and hence what the riskiest uses may be. So back to the start of this risk assessment, the initial phase of this research involved identifying where there may be large quantities of PFAS compounds in Ireland. So as an output of this project, I've conducted a literature review of international literature to determine what PFAS is used in, how it's manufactured, and where the major sources are globally. And then I'm linking it to how and where we might find them in Ireland. So the waterproof and oil-proof properties means that PFAS compounds have many uses in multiple industries and everyday products. So the main sources of PFAS in Ireland can be broken down into anthropogenic, civil, municipal, industrial, and agricultural sources. So anthropogenic sources are anything that humans use, touch, or interact with on their day-to-day life. So this is probably what you've already heard of: Teflon pans, waterproof jackets, detergents, and food and drink packaging, even in some coffee cups. Civil sources generally involve the use of AFFFs or firefighting foams. So foams are often used at airports, fire stations, or military bases for training purposes. Municipal sources are the accumulation of waste from domestic, business, and industrial use. So in Ireland, solid wastes are predominantly either incinerated, recycled, or disposed of in landfills. A small proportion of solid wastes are made into solid recovered fuel. Organic food and widely biodegradable products are disposed of in compost facilities, and then sewage and other wastewaters are treated at wastewater treatment plants. Industrial sources reflect a significant input of PFAS into the environment. So known industries that use or process PFAS are chemical manufacturing plants, pharmaceuticals facilities, paper and wood processing plants, information and technology facilities, and data centers. So agricultural sources include herbicides, pesticides, and land spreading activities, including biosolids and some fertilizers. So once these sources were identified, we used EPA maps and ArcGIS Online to identify locations that hold industrial emissions licenses and pollutant release transfer registers with activities that could be consistent with the use of PFAS, such as surface treatment activities or pharmaceuticals. So on this map, it also has sites that have been registered under the POPs legislation that have greater than 50 kilograms of PFOA containing AFFFs. We used ArcGIS maps to identify firefighting stations, airports, and military bases. And then for municipal sources, we've included urban wastewater treatment plants, licensed waste facilities, including lined and unlined and hazardous waste management facilities, and hospitals. Agricultural sources are more difficult to locate as they are diffuse sources rather than point sources. So land use maps can give us an indication for where land spreading practices may be occurring or pesticides might be used. So using the Liffey Dublin Bay catchment as a case study, the next step is to remove some sources that may be considered to be low risk in their current space. So, for example, office buildings may have PFOA containing handheld fire extinguishers. However, these extinguishers may not be released into the environment unless they're used to extinguish a fire. So as such, they might be considered low risk. If we detect PFAS in the River Liffey, does this mean that it's coming from one of these sources? Not necessarily. So remember, PFAS is incredibly mobile and can travel long distances, so proximity isn't necessarily an indication of the source. So on to our next step, determining whether these sources have a pathway to get into the environment. If it won't be likely to get into the environment, then it's classified as a low risk use. If it can, then we need to figure out how. So the waste industry is discussed widely in literature for aiding in the bioaccumulation and transformation of PFAS in the environment. So PFAS compounds will pass through multiple waste streams or be applied directly to the ground in the case of firefighting foams and agricultural sources. Anthropogenic, industrial, and civil sources of PFAS will enter the municipal waste streams by either being disposed of or washed down the drain. So from the waste industry, PFAS can enter the environment via air emissions from incineration, leachate from landfills and compost facilities, water from outfalls, and land applications from compost and biosolids. Humans will then interact with the impacted environmental media via ground and surface water abstractions, contaminated animal products, contaminated produce, and even recreationally, such as sea swimming, which is quite popular in the Dublin Bay area. So we've taken our previously identified sources, removed the low risk sources, and determined what the predominant pathways of other uses may be. These have been classified as infrastructure, infiltration, or runoff, and some locations had multiple pathways, such as airports and landfills. So discharge locations such as stormwater overflows, stormwater drains, and sewer discharge locations have also been included. In addition to sewage being a pathway for anthropogenic sources of PFAS, such as shampoos and washed treated textiles, street runoff is also considered a major contributing source of PFAS to surface water bodies. So on this map, all of the sources that may use infrastructure as a pathway are included. So industrial effluent, stormwater drains, sewage, and wastewater treatment plants. PFAS can be used in an industrial setting, such as chemical manufacturing processes or chrome plating sprays, and these can be released into the environment as industrial effluent. In the Liffey Dublin Bay catchment, PFAS compounds can be directly discharged into water bodies via infrastructure. Sometimes they're treated and sometimes they're not. So urban wastewater treatment plants are also included in the green dots on this map, as unless a wastewater treatment plant is designed for quaternary treatment, it likely does not remove PFAS from effluent. As a result, industrial effluent and wastewater treatment plants can release large loads of PFAS into surface water bodies. Other pathways are via overland flow or runoff and infiltration. These pathways are mainly relevant for sources interacting with the ground directly, such as firefighting activities, military bases, landfills, and agriculture. Overland flow is driven by land use, surface type, permeability, and artificial drainage. For example, firefighting foams are used directly. If firefighting foams are used directly on a concrete surface, then the predominant pathway will be runoff. But if it is used on an agricultural area, it is likely going to enter the underlying groundwater body via infiltration. So the land use and surface type can be determined using the Careen map. And then infiltration is also driven by land use in the map on the right, but also by groundwater vulnerability, depth to bedrock, and soil type, which is found on the GSI maps. Firefighting foams used in an extreme vulnerability area is considered a high-risk use compared to using it where there may be a thick clay subsoil and a large depth to bedrock. So the final step is to determine where PFAS is found in the environment and where there are linkages to our most sensitive receptors. So in the Liffey Dublin Bay catchment, the major receptor or sink is the River Liffey and Dublin Bay. In terms of ecological receptors, we have the Dublin Bay biosphere, which is a special area of conservation. Marine biota are considered to be some of the most sensitive receptors to PFAS, as if they are living within a contaminated water body, their entire food source will be also contaminated. And as for human receptors, we can identify potential exposure sites by using public supply source protection areas for drinking water and protected shellfish areas for consumption. So food and water are considered to be the major exposure routes for humans, and having a variety of food and water sources can reduce our exposure. So we've got our sources, our pathways, and our receptors. So the next question is, of the 4,700 plus PFAS, which one will we find? How bad is it? And what are the major contributing sources to surface water contamination? So under the Water Framework Directive, the EPA has carried out water quality testing for PFAS and PFOA in surface water bodies across Ireland. So this map shows the locations of positive detections or above the laboratory limit of detection. The purple pentagon indicates just PFAS detections. The orange cross is just PFOA, and the thing that looks like a little house is both. The EPA has returned to some locations to test for a larger suite of 44 PFAS compounds, and they are shown with the green cross. At the moment, we're interested in the occurrence of compounds, so where it's been found and what has been found, rather than the concentrations, as it indicates that there are many SPR linkages across the country. So we found these positive detections. Surely it's easy to figure out where it's coming from. The answer is no, it's not easy. So if we work backwards, the PFAS we find in the surface water body is dependent on a number of factors. So one is the environmental factors. So how close is our sample to a source? And then it's also dependent on river flow. So remember, PFAS can travel long distances. So we can look at river flow and dimensions of rivers to have a look at how far the PFAS could have traveled. So other temporal factors such as rainfall data, So heavier rain might mobilize more agricultural runoff, so from pesticides and biosolids, but it can also dilute the concentrations of PFAS in surface water bodies. So that's something else to look at. So chemical factors, some precursor compounds can break down into what we call terminal products, such as PFAS and PFOA. And this can give us an indication as to how old the contamination might be or how it might have broken down in the environment. Each of the compounds also has different dispersion, sorption, bioavailability, and solubility rates. So heavier PFAS compounds are less soluble and may preferentially sorb onto sediment, which may mean that you'll find lighter PFAS compounds in the water matrix. Similarly, marine biota may also uptake certain compounds over others, which may affect the concentrations that we see in the water matrix. And then the last factor is practical factors. So some compounds such as PFAS and PFOA, which we might have heard about everywhere, are more tested for in the environment as they're more relevant at the moment from a toxicological perspective. So just testing for 2 compounds may mean that we're missing critical and emerging compounds such as Gen X that may be in higher concentrations. The type of laboratory technique used will also impact the PFAS that you'll find. So laboratory techniques and research are catching up to the rate of new PFAS being created. So just because we might not be able to detect it, it doesn't mean that it's not there. So my colleague Helen later will be discussing this in detail. So there are lots of different subgroups of PFAS, but the most tested for are your PFCAs on the left, such as PFOA, and your PFSAs, such as PFAS, which will generally be the breakdown products of larger compounds or be a compound in itself. I've gotten this table or this flowchart from the Interstate Technology Regulatory Council from America, and there's a lot of great resources on that website as well. And the type of PFAS or the ratios of different compound groups can give us a clue as to where it may be coming from. For example, firefighting foams and wastewater treatment plants tend to have higher percentages of PFSAs in comparison to PFCAs, whereas street runoff and some industrial sources, as shown in the right, tend to have higher percentages of PFCAs. Now we have all the information, we need to see what's happening on the ground. So up there, that's Helen and myself on a boat on the River Liffey. We headed out to take surface water samples along the Liffey and some biota samples in one location. We were targeting some areas of potential sources. We're currently processing the results, but have started to see trends similar to those highlighted in the last slide. So in the lower Liffey, where there are some outfalls linked to waste, we have identified higher percentages of PFSAs in comparison to PFCAs. And in the centre of town around Temple Bar, we've found larger concentrations of PFCAs, which is expected due to the large number of stormwater drains. So we've also identified some unique compounds in the upper region of the tidal extent, which could be linked to unique industries found in that area. And in the biota sample taken around SP4, we're analysing the compounds found in different trophic levels, such as in algae and mussels, to see whether they uptake certain compounds or whether they filter it. So we've also taken samples across Ireland in other surface water bodies, in soil, sediment, and in groundwater wells. Some have been taken as background samples, and others have been taken to test hypotheses regarding potential sources. We've also engaged with citizens across the country to obtain samples from their local surface water bodies to get a larger spread of results. And we'll be running another citizen science project in August. So if you want to get involved, you can follow the DCU Water Institute page on LinkedIn for August. So yeah, that's me. Thanks for listening.
Great, thanks, Leila, that's great. Are you okay to share your slides then, Helen?
Can you see that okay?
It's just coming up, not just yet. Yeah, there we are. That's perfect. Thanks.
Okay, perfect. So my name is Helen Burke, and I'm a second-year PhD student in DCU working as part of the Invest PFAS project with the EPA. As Leila mentioned, this is a collaborative project between DCU, the University of Birmingham, and Arup. This project aims to investigate PFAS from source to sink to assess risk and inform PFAS strategy here in Ireland. My part of the project as a PhD student is to work on developing sample preparation and analytical techniques for the detection of PFAS in environmental samples alongside the University of Birmingham. So today I'll be discussing how to detect per and polyfluoroalkyl substances in the environment. So in case anyone missed the beginning of Leila's presentation, I'll quickly run through an introduction to PFAS again. So PFAS is an abbreviation for per and polyfluoroalkyl substances, and these substances consist of a fully or partially fluorinated carbon backbone attached to a functional group. So different PFAS will have varying lengths of this carbon backbone, as well as different numbers of fluorines along that backbone, and different functional groups as well. So on this slide here, we have an example of PFOA, which has a carboxylate functional group. And so it is part of the perfluorocarboxylic acids, or PFCAs, that Leila has mentioned previously. And other common functional groups include sulfonic acids, of which PFAS would be an example. And these different functional groups can govern the chemical behavior and, of course, classification. This structure contributes to their water and lipid resistant properties, and the carbon-fluorine bond is incredibly strong, rendering them resistant to degradation. As of 2021, the OECD defines PFAS as any compound containing a carbon bonded to 2 or 3 fluorines, and with this update, there's believed to be between tens of thousands to even possibly millions of these substances in existence. So PFAS are a group of man-made compounds accidentally discovered by a DuPont worker in the late 1930s. Teflon was first shot to fame in the 1940s when it was used in non-stick cookware. PFAS are now applied across a range of industrial applications, as well as in firefighting foams, textiles, and personal care products, as Leila has mentioned. And due to their widespread use, PFAS are now ubiquitous in the environment and have been detected in a range of environmental samples, including soil, sediments, surface waters, marine waters, where they're capable of long-range transport. So today I'm going to walk you through how we analyze PFAS in water samples, from sample collection through to sample extraction and PFAS detection. So the first step to detecting PFAS in environmental samples is, of course, collecting the sample itself. So here we have some photographs of our sampling activities during this project. So far, we have been sampling out on the Liffey, as Leila has highlighted in her presentation. We've also collected samples from other surface waters across the country, along with groundwater samples, and we're soon to begin works on soil samples as well. So performing this first step of collecting samples correctly is vital in order to attain representative results. And as I've mentioned, PFAS are now ubiquitous in everyday life. So they're found in many personal care products and are coated onto textiles. So there are a number of precautions that should be taken when carrying out sampling campaigns for PFAS analysis in order to avoid sample contamination. So here we have a graphic highlighting materials to be aware of. So a lot of equipment used in environmental sampling is made to withstand rough usage, so being dunked into rough waters and through dirty sediment. So we have to be vigilant around what materials we are bringing out into the field when we're sampling. We want to avoid any equipment that is coated in PTFE or Teflon, and avoid sample collection bottles that may have Teflon coated lids. So for collection of samples for PFAS analysis, we opt for high density polyethylene or polypropylene bottles and use powderless nitrile gloves during collection. And in terms of clothing, again, a lot of outdoor gear is often covered in PFAS-laden coatings in order to withstand heavy rains and treading through mud. During sampling, we want to avoid these coatings like Gore-Tex and Scotchgard and instead opt for more natural fibres where possible and PFAS-free synthetic materials. So currently there are a range of outdoor clothing brands that are now bringing out fluorocarbon-free rain gear, so this can also be an option. Other items to be aware of which have the potential to cause sample contamination include food packaging, aluminium foil, insect repellent, and some sunscreens. And even when taking all of these precautions, we should always collect a field blank on site. This is where we decant a bottle of high-grade PFAS-free water into a sample collection bottle. Ideally, we want our field blank to be the same volume as our sample volume, which, depending on a sample type for water, it ranges from 250 to 1,000 mils. This field blank is then brought back to the lab and analysed alongside real samples to screen for any potential contamination during sampling activities. So on this graphic, I've also referenced the Michigan Department of Environment, and they have a great general PFAS sampling guideline that goes into further detail on what materials are safe to use, what materials should be avoided, and generally materials that you should be cautious of when going out to sample for PFAS. So here I've just highlighted a picture of me in the field wearing my fluorocarbon-free raincoat, nitrile gloves, and cotton and natural fibre materials as well. So decontamination of equipment is another important step in sample collection. Sample collection bottles made of high-density polyethylene or polypropylene, as well as stainless steel collection equipment, are all decontaminated in the laboratory prior to going out into the field. So our lab decontamination steps include first washing all items with Liquinox soap. So this is PFAS-free soap. And following this, all items are triple rinsed with deionized water, followed by a triple rinse of methanolic ammonia solution, and finally a triple rinse of high-grade methanol. And once out in the field, equipment such as extendable sample collection poles, water pumps used for groundwater collection, and stainless steel tools are decontaminated between each sample site. So this procedure involves, again, rinsing with PFAS-free soap, Liquinox. Stainless steel equipment is scrubbed where necessary, followed by a triple rinse with deionized water and a final triple rinse of high-grade methanol. So we have found these decontamination procedures to be adequate following the analysis of field blanks collected following these steps. So although these decontamination procedures take a significant amount of time during the sample collection stages, they are necessary to avoid sample contamination. So out of interest, we tested field blanks that were collected as part of a different surface water sampling campaign. Sampling activities were carried out without taking the necessary PFAS precautions, such as avoiding PFAS coated clothing and personal care products. So without these precautions, in a number of field blanks, we found as high as 30 of the 37 PFAS we tested for were detected in field blank, with particularly high levels of 6,2-FTS and 6,2-DIPAP, both of which are associated with cosmetic and personal care products, and 6,2-DIPAP in particular being associated with food packaging and paper products such as toilet paper. So this goes to show the extent of which samples can be contaminated by everyday products when those collecting samples are not particularly aware of materials that should be avoided. So now we covered sample collection and issues surrounding contamination there. Let's move on to the extraction process that takes place when we return to the lab. So once back in the lab, we want to clean up our samples and concentrate any analytes that may be present so that we can easily detect them using our instrumentation. To do this, we use solid phase extraction, or SPE. So before running our samples through SBE, we first vacuum filter to remove any particulate matter that may cause blockages in our SBE cartridges. In our lab, for our PFAS methods applied to surface water and groundwater, we have found extracting a volume of 300 mL of water to be sufficient in concentrating PFAS so that they can be detected by our instrumentation. So that is the volume that we apply here in SBE. So SBE involves running, in our case, a water sample through an appropriate sorbent so that all the analytes of interest can be collected in a concentrated state. So before loading our sample, we first need to condition our cartridges so that the PFAS can bind to the sorbent. These cartridges contain a sorbent, that is a material that retains our analytes, and these sorbents bind to PFAS via hydrophobic interactions. So remember, as Leila mentioned, the fluorinated carbon backbone is hydrophobic, so they can be retained this way on the sorbent, and PFAS can also bind to the sorbent via anion exchange. That is where the functional group of the PFAS, which I mentioned in the first slide, binds to the sorbent. So in order to activate the sorbent so that this binding can take place, we condition the cartridge by rinsing through 5 mL of 0.5% methanolic ammonia solution, followed by 5 mL of methanol and 5 mL of acidified PFAS-free water. We then load our 300 mL of water into the cartridge. As this sample flows through the cartridge at a steady rate, PFAS analytes as well as some impurities bind to the sorbent, as you can see here in this graphic. We then wash the sorbent by flushing through 5 mL of PFAS-free water to carry out some impurities from the sorbent. And in the final elution step, we wash out and catch our PFAS analytes in a collection vial using 5 mL of methanol, followed by 5 mL of 0.5% methanolic ammonia solution. So now we have our clean concentrated sample extract. We further concentrate it by drying it under nitrogen and then reconstituting it in 1 mL of solvent. So we've gone from a 300 mL sample to a 1 mL sample extract. So we've concentrated any of our analytes that are in our sample by about 300 times. And the final step before analyzing our sample, we push it through a 0.2 micron syringe filter to remove any fine particulates that may remain, because we don't want to damage our instrument with these with this particulate matter. And at this step, I'll highlight the importance of watching out for contamination in the lab, as during my method development, I was finding contamination to be an issue at this initial syringe filter step. In particular, I found 6,2 FTS and PFDA to be contaminating my blanks during this step. And 6,2 FTS is used in the production of plastic and rubber. So I tested a range of other consumables from different brands until I found one that didn't contaminate my blanks. So this just goes to show that contamination can happen at any stage during the PFAS analysis. So we have covered sample collection of water samples as well as extraction of water samples. So now let's take a look at instrumental analysis. So the limit of detection is the lowest concentration of an analyte, in our case PFAS, that can be reliably and reproducibly detected using an analytical method. So this limit of detection is dependent on a number of things, including instrument sensitivity. We want a sensitive instrument that can generate high signal for our analytes so that we can detect low concentrations. Method validation, including optimizing instrumental parameters, as well as adequate sample preparation to reduce background noise from any dirty samples. We also focus on recovery studies to ensure that low levels of PFAS can be detected consistently in sample replicates, and quality control measures such as laboratory and field blanks all aid in determining the method's true LOD. And sample type as well. So different sample types can have an impact on LOD. Essentially, dirtier samples can interfere with PFAS detection, as high levels of organic matter and other chemical interferences present in complex samples such as wastewater, sediment, can interfere with instrument readings, which raises the limit of detection. And when looking at carrying out target analysis, where we are looking to detect a known list of compounds, we want to aim for limits of detection and in turn limits of quantification that align with or that align with or even better are below the limits set in regulations. So let's take a quick look at regulations relevant to Ireland today. So Irish drinking water PFAS limits are set to come into effect in 2026, in which a sum of 20 PFAS listed in the table here on the left-hand side is to have a limit of 0.1 micrograms per litre and a limit of 0.5 micrograms per litre for total PFAS. So that is the totality of PFAS detected during sample analysis. So if labs can analyse for more than these 20 PFAS listed on the left, the limit of all PFAS present in drinking water that can be detected by any one method is 0.5 micrograms per litre. The EU surface water guidelines also contain some PFAS limits, with an inland water PFAS limit of 0.65 nanograms per litre and other surface waters having PFAS limit of 0.13 nanograms per litre. The EU methods of analysis guidelines also provide relevant limits of quantification, that is, the lowest concentration of an analyte that can be quantified accurately, with LOQs of individual substances required to be 1.5 nanograms or lower, and LOQs of PFAS of high concern, so that is PFOS, PFOA, PFHXS and PFNA, required to be well below that 1.9 nanograms per litre. So how low can we go in transitional waters with a 300 ml sample? So on the left in the green, we have our method LODs and LOQs for PFAS relevant to incoming Irish regulations. And on the right, we have some additional PFAS compounds that we target that go beyond that initial list of 20. So by concentrating our 300 ml transitional water samples by 300 times, we acquire LODs ranging from 0.005 to 0.36 nanograms per litre. So we can see these compounds are in our samples at these levels. And with our LOQs, we can confidently quantify between 0.015 to 1.08 nanograms per litre across our 33 analyte list. And with these limits, we're aligning with those regulatory requirements. And for groundwater, how low can we go with a 300 ml sample? Again, by concentrating 300 ml of groundwater samples, we acquire LODs ranging from 0.003 to 0.139 nanograms per litre, and LOQs ranging from 0.1 to 0.42 nanograms per litre. So with the groundwater samples, we can achieve much lower LODs and LOQs, as this is considered a slightly cleaner sample type when compared to those transitional waters. As transitional waters can, of course, contain a range of organic matter, including biological matter, which can interfere with analyte detection. So with that, I'm afraid I can't quite share any interesting results with you just yet, but you can keep an eye out for some results that will hopefully be out in the coming months. And this includes a case study on the River Liffey, as Leila mentioned, as well as an investigation into PFAS found in biota retrieved from Dublin Bay, which should help tell a story of what PFAS are present in Irish waters and how these PFAS are entering biota that reside in these waters.
Great. Thanks a million, Helen. Thanks to Helen and Leila for two fantastic presentations. Oh,
sorry.
You're right. You still there? Can you hear me?
Yeah, I can hear you. I just can't see you.
Perfect. Just in, that's okay. You can see the screen. You can hear my voice. But anyway, just thanks very much, both Helen and Leila, for two fantastic presentations. If there are any questions, you can pop them into the Q&A chat there, and we can bring them to the ladies. So to start, I have one or two questions. Firstly, for Helen, so there were some very, very rigorous procedures and protocols in place when carrying out the sampling on site. What kind of concentrations were there in the samples that were taken when those measures weren't put in place? What kind of concentrations of PFAS?
When they weren't put in place, we are finding concentrations in field blanks ranging from 90 nanograms per litre, and one field blank even had nearly 500 nanograms per litre, mostly being attributed to those two contaminants, the field contaminants that I mentioned initially, 6,2-FTS and 6,2-DIPAP.
Okay, well, that's quite significant. And so that's my other question then. Were there any samples that had absolutely no PFAS? Zero?
No, so far we haven't come across any samples that have zero PFAS, no.
Yeah. And your blanks, I presume some of your blank samples had absolutely zero.
Oh, the blank samples, yeah. But the actual real samples, they all have had PFAS in them so far.
Okay, well, it's comforting to know actually that at least, with the right measures in place, that cross-contamination can be completely prevented. So that's great. And just that we have a question in there as well. Someone's wondering, do you know of any sort of online resource or app which shows whether or not a personal care product includes PFAS? Have you come across that, Helen or Leila?
I haven't come across an app, but I know that so there's the California State Water Board sampling guidelines. They have a couple of links in there to, I know, I think then they send you on to the Michigan guidelines that have sunscreens and insect repellents that are PFAS free. And there's also another link in there to the environmental working group that I haven't looked into it too much, but it's sort of a page that leads you about the cosmetics and things like that. So I can send those links on.
Oh, great. Yeah, okay, that's fantastic. Thanks, Leila. I have a couple of questions in there. So the biofilm sample taken from the liffey, was PFAS much higher in that sample compared to surrounding waters, and any idea of its source?
So for the biofilm samples, they actually haven't been fully analysed yet, and they're being analysed using a screening method and non-targeted analysis as opposed to targeted. So we won't have a precise quantifiable concentrations for those biota samples. But again, they're not fully analysed yet, so we're still working on them.
Great, thanks, Emil. Sorry, another question coming in here. So do you know from your research, what are the most critical health effects linked to PFAS exposure? And is there a safe threshold? Have you come across anything in your reading or literature reviews?
Yeah, so in terms of the safe threshold, there is a tolerable weekly intake, which I think is from the European Food Board, and I can't remember off the top of my head, but it is, I think it's 4.4 something nanograms per kilogram per week. So yeah, that's kind of it at the moment. And sorry, what was what was the first part of the question?
No, I think that's it.
Oh, that was it. Okay.
The critical the critical health effects. I mean, that's very hard to say. That probably didn't come up in your research.
Yeah, that's not really within the scope of our research. We haven't been looking at human receptors. But yeah. Perfect.
And then, is there any indication how compliant Irish drinking water is currently against the prospective PFAS standards?
We haven't been, as part of this project, we haven't been testing drinking water, and I believe some water companies are testing for it, but as they have to become compliant by January, but I don't believe that information has been released publicly.
Okay. And then Brian Gargan, I'm not completely sure which parameter Brian is referring to here, but you might know. So should the additional parameter which you tested, which aren't in the EU drinking water regs, be added into the suite?
Can you repeat that question?
Did you test for an additional parameter which isn't included in the, so I think you had like maybe the 20 parameters and then you had additional parameters?
Oh, we have additional analytes that are beyond the 20 suite. Yeah, we do.
They were finding quite reasonable concentrations, were they? Some of them at least.
Yeah, so some of those additional analytes were some of the main analytes that we found in those contaminated field blanks where precautions weren't being put into place. So they're definitely around, even though they're not a part of that 20 list.
Yeah, it's interesting. I wonder perhaps in the future they might be included in the list.
Yeah, exactly.
Yeah, okay. Do you know of any research into a more scalable detection method for detecting PFAS? Are these drinking water standards are being brought? The drinking water standards are being brought in. Are they likely that many Are these drinking water standards being brought in? Companies perform PFAS detection on a larger scale. So I guess this comes down to, is PFAS being detected at the moment widely out there? Is it being analysed and detected at these levels?
In drinking water?
Yeah, I think again, this comes back to the drinking water, which I think wasn't really what you were looking at so much. But I guess, a lot of the groundwater stuff will probably lead into the drinking water stuff. I guess the drinking water will be very, very clean. It'll be the cleanest. So maybe the groundwater stuff is the most comparable. But again, that probably is a little bit left of what you were looking at there. Did you come across many labs or things that that are getting similar detection levels to yourselves, or did you look at that? Because your detection levels were really quite good, quite sensitive.
Yeah, so we are working in collaboration with the University of Birmingham. Stuart Harrod and Yulong Ma have put out a number of studies testing different sample types, and they are also achieving really good LODs as well across different sample types.
Perfect. So do you have any ideas about the solution to the problem? That's it. In your opinion, from your reading, apart from education or public awareness, say source prevention, the waste looked to be a big piece there. Is kind of intervening at the waste point going to be part of the solution, or is some way of treating, like devising techno-optimism, finding a way to treat the problem? What's your opinion on that?
Yeah, so obviously waste intervention, particularly wastewater treatment plants and industrial treatment plants, that's quite important to, number one, test to see whether it's there. And then there are remediation methods or treatment methods as well that you can use to remove it. I think also a really important one that the EPA is doing at the moment is banning of PFOA containing firefighting foams. So that's really important to look at what firefighting foams, that you may have on site, looking at their data sheet, seeing whether they contain PFAS, and they may say that they're PFOA free or PFOS free, but that means that they could have other PFAS in them. There was a ban of PFAS in the early noughties, but it meant that people, like other companies, were creating other PFAS, and that's become an issue. So it's just really important to transition to fluorine free foams rather than PFOA or PFAS free foams as well.
Great, thanks very much, Leila. And then Helen, I think this is one for you. So when you were collecting samples, were they stored in cool boxes and out of direct sunlight? Also, are the liquid samples and vials filled to have no airspace?
Yeah, so once we collect them, we keep them in a cooler box, and they are kept away from the light because we collect them in those brown Aslan bottles that I showed earlier on in my slides. And yeah, so because we freeze our samples once we bring them back to the lab, we need to leave some headspace just so that the bottles don't end up cracking once they're frozen. Then we couldn't really analyze them accurately once that happened.
Great, thanks, Helen. This is another one for you, Helen, I think. So how long can samples, or how long were you storing your samples between collection and analysis? And I think you said there you were freezing them. Was that kind of the method? They were frozen until they were analysed?
Yeah, so we've been freezing them until they're until we analyze them. And there's a number of studies that test how well PFAS samples can be stored and accurately measured, and freezing and being kept frozen in the dark is the best way to do that.
Great, thanks. So Max there is noting that, I suppose, obviously there's a waste is circulating PFAS, and did you come across in wastewater treatment plants, are PFAS routinely monitored? Is that something that you encountered?
I'm not sure about in Ireland yet. I've come across a lot of studies in the US where they're testing biosolids and effluent as well. They're quite far ahead in the technology of then treating it as well. So looking to them and I'm looking at the concentrations in the biosolids. Stuart Harrod and Yulong Ma have recently released a paper with biosolid concentrations, or at least it's it's happening soon, but it's biosolid concentrations in Ireland, and they are quite similar to those in the US. So there's no, and the rest of Europe. So yeah, and if they're treating it, then maybe we should be treating it as well.
Yeah, perfect. Thanks, Leila. And then I'll just take one last question. So you mentioned, Leila, that you were taking some biota samples, and Finbar quickly there is wondering, has there a link between PFAS and ecosystem health? Has that been established, or is that just an active area of research at the moment?
I think it's an active area of research. I think, there's, as we've seen with some of our concentrations in the biota, you find it in certain trophic levels as opposed to other ones, and it can impact different animals as well. So it can impact reproduction rates and things like that. So I don't know if it's been directly linked to ecosystem health as such, but they have seen that it can affect reproduction and stuff like that. So not great.
Great. That's perfect. Thanks very much there, Leila. Great. Okay, so just a huge thank you to both Leila and Helen for two absolutely fantastic presentations. Super, super interesting. I've just got a few last slides to go through. Whoops, that's the wrong screen. A few last slides to run through. So the first one is just some upcoming CIWEM events. So CIWEM Republic of Ireland, in collaboration with Engineers Ireland, are running an in-person event on the 9th of May. Looking at embedding resilience in water and flood management infrastructure. And there are still places available on that, and it's for an absolute steal of only €30. So if you're interested, please do come along. And then the wider CIWEM group have lots of events, and the next few that are coming up are listed on the lower part of the slide. And then particularly CIWEM have lots of learning and development opportunities. We've got a link included just there, lots of publications, and in particular there's a journal of flood risk management, the Water and Environment Journal, and the Environment magazine. And just to say as well, the CIWEM RI branch are always welcoming of anyone that would like to join our committee. So if you're interested, please drop us a link on LinkedIn. And a huge thank you as well to Barbara Woods. So Barbara Woods does all of the background work, and puts a lot of time and energy into organising these webinars, and is much of, if all of the reason that these webinars are so smoothly. So a massive thank you to Leila, Helen, and Barbara. Lovely. Thanks very much, everyone. Take care. Enjoy the rest of your day.
Thanks.
Thank you.